Hi, everybody. My name is Curtis Vogt, and I work with Beacon Biosignals. Today, I'm going to talk about the prototype Julia project, Ray.jl. So, Beacon has been using distributed computing for some time now, and mainly we use distributed.jl for this purpose. And we've run into kind of a few challenges as we've done this, but we've also developed some in-house tooling as we've kind of gone along. Yeah, some of the user stories we've identified we wanted to kind of solve was we wanted to be able to deal with ingesting large amounts of semi-structured data, dealing with exploratory workloads on large time series data, and also workflow orchestration for our inference pipelines. A couple different tools we ended up looking into as part of this work is we looked into Apache Beam, Spark, also Argo workflows, transducers.jl, and actors.jl. Ultimately, we decided to do, we tinkered with all of these tools, but we ended up doing deeper dives into both Ray for Python and with Dagger.jl. As part of this work, we also realized that using toy data sets, using toy kind of problems to put into the distributed frameworks only got you so far, and we needed kind of like a realistic benchmark in order to get realistic results. So what we ended up choosing for that realistic benchmark was using EEG spectral features. It's a realistic workload for Beacon Biosignals. And it was also simple enough that we could port it to different programming languages without it being too much of a hassle. Sorry for the blinking there. Eventually, we ended up continuing using Ray and not Dagger.jl. I'll get onto the reasons for this in just a little bit. And kind of one of the milestones we accomplished with this work early on is in order to see if we wanted to use either continue with Ray in Python or Ray in Julia, was us using Julia and calling the C++ shared library that Ray provides in order to store data in their object store and then retrieve that data back out. So with kind of some proof of concepts to prove that we could kind of work with Ray in Julia, we ended up working on this Ray.jl MVP focused on the real-world benchmark. So I need to answer now why we didn't go with Dagger in the end. And so basically, during our experimentation, we just ran into a lot of issues. And kind of a big concern for us was that it was hard to debug these problems. And we have a lot of kind of users in-house that are less experienced with Julia, and we didn't want kind of the pain points of trying to teach them all of the nuances of having to deal with Dagger.jl. Also, Dagger uses distributed.jl, and that turned out to be a lot of where our problems were kind of coming from. Ultimately, what we wanted is something where you could submit a workload and then have the cluster automatically scale up to fulfill that workload. Also, Ray just had some interesting features that we really wanted to kind of look into. One was the shared memory system it had. It's object store, and some features I'll talk about in a second there. And it had that automatic resource scaling we were talking about. So that was something we really wanted to look into. And finally, the ultimate reason was that it was just kind of more battle tested. So the whole idea of this Ray.jl MVP would be we would have to write kind of the front end for Julia, but the back end would end up being entirely what existed. And so we didn't have to write that stuff ourselves, and we could get kind of the reliability for free there. So I need to talk about some key concepts in Ray kind of before I proceed here. Basically, a Ray task is just a regular Python function, a non-class function that you execute kind of remotely on a Ray worker. There are actors. This is basically, you can think of as a stateful function. Specifically in Python, how this works is you take an instance of a class. That instance gets assigned to a specific Ray worker, and then any method you call on that instance are then run against that one specific worker. And then so you get a stateful-based implementation. We didn't end up implementing that in Ray.jl. That's mainly because the MVP didn't require it. But we did identify that multiple dispatch was a unique challenge to get this implemented. Additionally, there's objects. They're immutable, and they get stored in Ray's distributed shared memory. And you can also specify resource requirements for both tasks and actors. So you can say how many CPUs that this kind of function requires, how many GPUs, and there's memory restrictions. And that's useful for the Ray scheduler in order to both assign your workload to a node that can fulfill those requirements. And also, it's good for the auto scheduler for being able to bring up the right amount of resources. So I need to talk about Ray objects. Once again, they're immutable. That is important properties for the object store and how it kind of manages them. And also, it has the capability to do zero copy reads. So in Python, if you're specifically working with a NumPy array, what you can end up doing is storing like a multi-gigabyte array in the object store, and then you can have multiple array worker processes in Python read and index into that data with only having the one copy in memory and not having to copy that data into the individual worker process memory. The object store, also some properties you need to know, include it's distributed in that every Ray node has a copy of the object store, and that it uses reference counting for dealing with garbage collection. That's an important detail for the client side, because if you don't implement that properly, your objects could disappear on you. And also, it had some nice fault tolerance capabilities. So if your node would suddenly, your Ray node would suddenly get terminated, the associated object store is also terminated, and objects in there are lost. But it can end up recovering that data by looking at other object stores, or alternatively, if there isn't any copy stored, it can end up rerunning a task in order to reproduce the result and automatically recover. So on the client side, you don't end up working with Ray objects, you work with object references. And those are created in two different ways. One is with Ray.put, where if you want to store kind of your own user data in there, you can put whatever you want in there. And the more common way is when you create a Ray task. So every time you make a Ray task, the return result of that is an object reference. These are very similar to distributed.jl's future type, specifically in that they can reference data that has not yet been created. So when you make a Ray task, you end up getting an object reference back, and that object reference may point to some unfulfilled data, and then only when you need to retrieve the content of that data does the call block, and then you end up having to wait. These references can also be passed between workers. So once again, if you submit a task, you can pass in that object reference as a parameter to that task. So I'm going to talk a little bit about installing Ray at the moment. Unfortunately, it's not as easy as just doing a package.add. And mainly that's because there's some complications around kind of our binary builder setup that we have to resolve yet. But the things you need to know is basically follow the instructions at the bottom of the slide here, and be sure you're using the dev instructions and not the stable ones, because I did a bunch of corrections recently. And then the other details are that specifically you need to use a version of Python between 3.7 and 3.11, and a version of Julia between 1.8 and 1.9. Those are just restrictions right now. We're trying to solve all that. We also haven't registered the package with General, and that's because we kind of want to sort out this mess before it's actually registered. So now for the examples. So here's an example in both Python and in Julia for storing data in the object store. So it's pretty simple. We end up taking your user data, put it in the object store with a Ray put call, and then end up retrieving it with a Ray get call. So you can see the interfaces between Python and Julia here are very similar. And ultimately, the Python design worked in Julia well, so we just copied that over. And then what you need to know on the Julia side is that we end up using Julia's serialization standard library for storing data in the in the object store. So basically anything that's serializable will work here. As for tasks, here's an example in Python. And so basically the basic line by line here is we end up initializing this Python process as a Ray worker. We then define a Ray task definition, that square function, and then we end up executing that Ray task with 4 different input values. And then we get back 4 different object references, and all these tasks end up running asynchronously, and then only when we call the Ray get call, we have to block and wait for the results here. The important details here is one is that Ray.remote decorator at the top of the square function. That ends up translating the Python function definition into the Ray task definition. The important part of this is basically you can't run square as a regular Python function here. So that's why we need that .remote syntax there, because it's disallowed to just call it a square. In Julia, that was actually something we wanted to get away from. We wanted to be able to call any arbitrary Julia function as a Ray task. And so what we have here is we have this submit task function that we have, and this is intended to be a low-level interface for submitting Ray tasks. We haven't worked on a high-level interface for it, but basically this is mirroring the invoke syntax maybe used to. And then, yeah, it's the same thing again. We submit 4 different Ray tasks, end up getting the object references back, and then have to wait for the results. So here's a little bit more of a complicated version of this same thing, where we've updated the square function to now be able to dereference object references which are passed in. So the details here you need to know is we use Ray put in order to put some data into the object store. We then to have this list comprehension where we end up submitting 4 Ray tasks which take in object references back into the square function there. We need to dereference those objects in order to do the computation. They get returned, and then we get 4 more object references back, and then we get the values back and we can show it that way. But also, now because we can run square as a normal Julia function, we can do things like on the bottom. On the second last line, you can end up calling square as a normal Julia function, pass in those object references, have them be dereferenced, and then get the same values. And you can also pass in actual literal values and get the same results. And the way that works is the ray.get function works as the identity function if it's passed in a non-object reference. So back to the benchmark for a bit. So this is just a high-level overview of the EEG spectral features benchmark we ended up using. And so it's kind of 2 parts here. One is we ended up using a package we've open sourced called mocktablegenerators.jl, which ends up generating our input data we use for the algorithm. And that was a combination of arrow files that we generate and LPCM files. And the algorithm itself, what it does is it takes a time series data, splits it into segments or chunks, and then what we would do is we would compute some statistics on each of those chunks in parallel with Ray, and then we would take those statistics and calculate in parallel the features that we were interested in, and then ultimately end up reducing those into the final set of values. And so ultimately this is just a map reduce, but it was kind of a realistic workload and something we wanted to parallelize. So here's some of the results. So this is the total amount of time it took to run Ray and the original algorithm. The original algorithm there is in blue, and then the other colors are running on a single node Ray cluster with 4, 8, and 16 different workers. And we can see here there's some good speed up. This is the actual speed up graph. Same information again, just as a speed multiplier. We're actually getting a 12 times speed up for the 16 Ray worker cluster over the original results. And overall, this graph here is just basically saying or showing how much or that our benchmark is scaling quite well with the number of segments. Oh, something I neglected to share is that number of segments value at the bottom is basically we ended up running the algorithm over a different subset of segments, so we could run it on different resource-constrained environments, and then we could kind of extrapolate the results for how better things would be if we'd have even more segments. So this one here shows kind of the latency the Ray.jl package was introducing over the original algorithm. So the original here is actually the fastest because it doesn't have that kind of latency. And in the worst case scenario here, there was 8 seconds of latency, which is really not great for Ray, but on average, it ended up being 2. So as we would add performance improvements to Ray and kind of like fix Ray.jl, and as we would fix things, then we'd see these lines starting to converge. We also did some tests on multi-node clusters. So these graphs end up being a little busy, but the Ray local is a single node cluster. Ray cluster is the multi-node cluster, and the original is the original results. We also ended up doing some larger amounts of segments for a limited number of configurations. So we have 1,000 segments in this case for some. So here's the speed up graph again. Also, it's a little bit crazy here, and unfortunately some colors kind of are too close. But really the key takeaways from here is more vCPUs equals more speed. And basically, if you have the equivalent amount of vCPUs, then using fewer nodes is better. And ultimately, this makes sense because if you're dealing with multi-nodes, there's some cross-communication you kind of have to deal with. But even in the multi-node, we're seeing some really good speed up over the original. And then this graph shows the Ray latency again. And this one I think is actually particularly pretty interesting because even though with the multi-node cluster, we're seeing some serious extra latency being added, where you can see up to like 80 seconds of latency with the multi-node cluster. But as the workload increases, especially with 1,000 segments, we end up getting pretty close to the single node cluster performance and even the original performance. So basically, really what this shows is you shouldn't run the multi-node cluster if your workload sizes are way too small. It's not worth it. And you can see that, especially in the beginning, it's way worse. We also did an extra thing with a multi-node cluster. We kind of timed how long it took to spin things up. And so the time axis here is showing the time between when we submitted a Ray workload and then the total amount of time it took to get all the nodes online. And so the details here are when we used larger instances, it was a bit slower, but the difference between the smaller node instances and the larger node instances is about 4 seconds, 4 to 8 seconds. Not a huge difference, and ultimately it took 60 seconds. But something I should point out is this is an absolute worst case scenario, because as your Ray nodes would come online, the scheduler would automatically start scheduling work and start doing things. So depending on your workload, it may be good to use smaller nodes because they come online faster, and you can at least get some of your work started. Some additional findings that weren't included in the graph is that just this automatic scaling stuff ended up working really nice for our workload. Allowed kind of users to not have to think quite as hard about how many nodes do I have to bring up ahead of time in order to get these things done. Something I thought in particular that was really nice for cost savings was scaling down during execution was possible. So if you have a very bursty workload that needing a lot of nodes early on, but not so much later, because the Ray scheduler is aware of what nodes are actually being used and can scale down those nodes while the workload's still running. Additionally, the Ray resources are logical and not physical, so that can bite you if you end up saying your 16 vCPU node has 100 vCPUs. It'll overschedule in there and can cause things to crash. But it's also nice because you can give yourself a buffer and you can say my 16 vCPU node actually only has 12 CPUs on it, and that way you have a buffer if you didn't quite set your resource scheduling correctly. We also ran into some issues with memory during running these benchmarks. The problem there, we expected the Ray task would automatically retry when node had failure. We thought we had some memory leaks going on, and that we should just have it automatically reschedule. That just turned out to be a bug in the Ray.jl code, and we've since fixed that problem. So we have automatic retries, and those kind of failures were less annoying. Oh, I have a little bit of time still. It's good, so I can get to some tangents. So something we ran into, and you may have noticed before, I was just using anonymous functions in the examples. And the reason for that is because when you're dealing with serializing named functions in Julia, they're done strictly by the name. So you don't actually get the contents of the function definition. And so this was problematic for functions that were defined on the REPL. You couldn't actually serialize them and then send them over to the other workers. But those familiar with the distributed.jl may wonder, well, how does that work? Because it does that. And it turns out they don't use the base serializer. There's a custom cluster serializer that what it does is it tracks global references and automatically keeps things up to sync as they get changed. We also require a custom serializer, but for our needs, that's for dealing with the reference counting, because we need to know when object references are embedded inside of other object references, and so we need to kind of indicate that information. So we ended up doing some soul searching, and we're wondering if we really needed to support globals for this MVP. It turned out we didn't, for the most part. We didn't want closures, but we did want to deal with named functions in some form. So we kind of went about it in a different way. The problem with the whole closure setup is kind of this, is if you look at this example, which doesn't work in Ray.jl, try to consider what you expect would happen. So if you have 4 Ray workers, would you expect that all the workers would have the global X initialized to 0 in all of them, and so the result of this call count for all these would be 1? Or maybe you would expect that X would be shared across the environment, and that meant the last executed task should always be 4. Now, the problem with doing that last one is it ends up being really expensive for sharing that information and keep it in sync, and it's something we weren't really interested in doing. I think probably the former of saying, hey, they all initialize to 0 would be more reasonable, but it's something we didn't need to tackle, so we just said, this is kind of crazy. We did want the named functions, though. So this is the solution we ended up going with. We have this Ray import macro, which is basically, we can say what packages we want to import before we initialize the Ray workers. So ultimately we just said, okay, we're not going to support named functions on the REPL for now, but we are going to support named functions within packages. So you can import and then use all your references that way. So it kind of forces you to use a better workflow than just entirely in the REPL. Although ultimately it'd be nice to have that for just experimental purposes. And then I have a little time to talk about this one. This was a problem we ran into during development of Ray.jl, where on our CI we would randomly see this error. And so there's two things going on here. One is there's this Ray buffer was deleted thing. This kind of indicated to us we may have messed up our reference counting, but that's kind of like a red herring. The real detail here is at the bottom, where further down the stack trace in some C output it says check failed, expected size 28, but expected size got data of size 17. So that we didn't really have a theory on what was going on there right away. But when we kind of dove into this a little more, it turns out that the thing it was complaining about was related to the owner address of an object. And so during the serialization process, there's a whole bunch of different pieces of information we needed. And during kind of like, we added some debug logs, and over time we realized that the problem here was that the IDs could contain null characters. And so that kind of made sense now finally why we were getting this size mismatch. So initially we ended up working around this by base 64 encoding the owner address on the C++ side, but then we wanted to look into deeper on what the actual problem here was. And so here's kind of an example of what was going on. So if you take this Julia string and you convert it into the CXX wraps standard string implementation, you get this kind of null terminated string. But then if you look at the characters inside of it, something weird's going on. That's not actually what it shows as the string. And then if we go a little further here and we go a little different, so it turns out that the C++ strings, unlike C strings, are not always null terminated. They have a number of code units associated with it, so you can actually have a length and include null characters in there if you want. So we tried using the CXX wrap interface for doing that after we learned about it, but it's still null terminated, which is a little weird. But then when we look at the actual character list, well, we suddenly see our null character, which is good, but the rest of the characters are all messed up. So what was going on here? Well, here's kind of another example. We kind of had this theory that maybe what was going on was just the display was messed up, and it wasn't actually like any characters were being messed up. But so we did a little further deep dive. So we're kind of doing this round trip between standard strings and strings. And so we said, okay, let's take our standard string with the number of endcone units, then convert it back to a string and see what the character list looks like. It's like, okay, so it's definitely null terminated here, right? That's what's going on. All right, let's do it again. This time let's take the character list from the standard string, convert it to a string, and then look at the character list. Well, we're back to our messed up character list. And that's what we said. Okay, another experiment. Let's take the character list of the standard string, convert it into a byte vector, then back into a string, then back into the character list, and finally we get our original data back. So it turned out the problem here ultimately was that the CXX wrap had an invalid implementations of is valid and iterate, and that was causing kind of this round trip thing to get messed up. And so it's fixed now as of CXX wrap 0.14.1, and so hooray, now you can actually do round trips between standard strings and strings. And the other thing is, though, it was kind of important to still have null terminated strings in certain cases, and so in the last little example there, if you're using a C string type, that one is still null terminated because it's supposed to be a C string, so it makes more sense. As for other things, there's a bunch of future work we want to do. One of the main ones is we want to incorporate the Julia language support into the official Ray project. We have a PR out for that. It's kind of stalled out though. It's only 200 lines of code, but the official Ray project maintainers, their kind of stance on it is they don't want to add any additional language support right now, which is unfortunate. But they did say they would reevaluate at the end of the year, so maybe we'll get somewhere there. The other thing is I'd like to make a proper JLL for this package. Array itself uses the Bazel build system, which does not play nice with Binary Builder. And Elliot last year promised me that Binary Builder 2 would solve all my problems, but at that time, during JuliaCon, he was like, I don't know if I'll even work on that. But lo and behold, it's happened, so maybe now I can fix that problem. And then some other things, just registering the package, a better high-level interface. I'd like to have some like automatic instantiation of Julia projects so you can have more of an interactive workflow with revise. And I think we can get zero-copy support in Julia using mmap, but that's something we need to look into further. And then obviously the stateless named function serialization support we'll want to add in. We'll basically probably end up using what cluster serializer ends up using, but something we also need to do. I will say that Beacon has since pivoted a little bit, so we're not working on this as actively as we used to, but I definitely want to try to push to work on this again because there's lots of interesting ideas here that I think the Julia community could end up using. There you go.
Thank you. Great talk. Two short questions. The first is, you mentioned that one disadvantage of Dagger is that it uses distributed. And what is Ray using? Is it using MPI? Can you share some light on that?
It uses its own thing.
Its own thing.
Yeah, so basically it has its own concept of how it kind of sets up clusters. So normally, the reason I mentioned before you need kind of Python installed is we usually end up starting the Ray cluster using the command line that needs our Julia version language support in it. And so basically, I'll start up kind of your head node and do it that way. For the multi-node support, they have a Ray clusters feature, and so we ended up using Docker containers, and that's kind of how we would like set up our initial node states. But it's kind of using its own thing, and then yeah, it's doing its own communication under the hood. And Ray itself, we're basically implementing the concept of Ray here called Ray Core, and Ray has a bunch of like machine learning training libraries built on top of that, and that's something we would eventually add in the Julia community once we had enough support for it, that kind of thing.
Sure, okay. And second short question, you had, I think the very first plot, but probably all of your scaling plots, they showed some kind of dip at, if I'm not mistaken, 50 segments.
Like that.
Any idea what's going on there? In particular, the first one, I think it was single node. Yeah, this one.
Yeah.
Any idea what's going on there?
I'll note I didn't run these ones directly. So we probably could have just ran more samples and what was going on. It could just happen to be that like this was some weird case of like the number of nodes and workload kind of being bad. But I wouldn't normally expect this. I'd expect normally this for Ray thing flatlining behavior. So I mainly just expect those to be outliers. But like these tests took a while to end up running. So yeah, basically if we ran them enough times, we probably wouldn't see that anymore.
All right, thank you.
So just a quick question on how the workers are being set up. So there's a Ray manager on each node, right? And it does spawn the Julia workers there, right?
Yeah. Yeah, so there's kind of like, there's some memory reserved for kind of like Ray managing itself. And that includes kind of that object store I talked about. And there's also just like some intercommunication setup there between the Ray stuff. I don't know the specific details of all that because I didn't have to look into all that. But yeah, there's some memory overhead there, but it handles spawning the Julia process for you. And we did that's part of some of the changes we did to the Ray official code, is telling it how to spawn Julia. We ended up making it very generic such that we could tweak from the Ray.jl code how the workers would end up spawning it.
Okay, thank you.
Welcome.